In the last video, I talked about identifying and summarizing data, and in this video, I'm going to talk about population distributions. So the population, we can think of this as the entire collection of objects of interest, whereas the sample is a subset from the population, hopefully, that's been randomly selected. The process of statistical thinking is drawing inferences about the population by using the sample data. And the connection between the sample and the population, that connecting piece is the model. And the model we can think of as a mathematical abstraction of the real world that we use to make statistical inferences. So there's a couple of assumptions that we need to make this whole statistical thinking work. One of these assumptions is that the model provides a reasonable fit to the sample data, and then the other assumption is that the sample is representative of the population. And so that's why we like to have the sample be a random subset of the population, so that it is representative. So one example of a model that comes up a lot in statistics and in regression modeling is the normal distribution. And this is a very simple model, but very effective. And you might have heard this referred to in the past as the bell curve. So we can visualize what a normal distribution looks like. And one way to do that is to think about what would happen to a histogram as the sample size increases. So if we have more and more data, then we can make the bars in a histogram narrower and narrower. And eventually we can think of the histogram as being smoothed out with a line going through the tops of all the bars. And if the data was coming from a normal distribution, then that smoothed out histogram would look like a normal curve or a bell curve. And so that's what this diagram here is illustrating. That as we increase the sample size, the histogram bars get narrower and narrower, and we can think about smoothing out the tops of the bars with a line, and that line represents the distribution of a normal distribution. So here is that normal density curve without the distraction of the histogram bars. And so this is what people have traditionally called a bell curve, because it kind of looks like a bell. But one distinguishing feature is that at the edges of the bell, see how the curve is coming down here closer and closer to the axis? It actually never reaches the axis. If we were to keep drawing it, it would never actually quite touch the axis. And on the upper tail too, never quite reaches the axis. So the way that we use this normal density curve is to calculate probabilities related to normal random variables. And so the way that we use the curve to do that is areas under the curve represent probabilities. And so the area under the entire curve, so from way out in the left tail to way out in the right tail, under the entire curve is an area of 1. And then in between specific points on the horizontal axis, if we calculate the areas between those points under the curve, then that tells us the probability that a standard normal random variable is between those two values on the horizontal axis. So here I've got an example where A, my left-hand number is 0, which is right in the middle of the curve, and B, my right-hand number is 1.96. So you can see the scale, the horizontal scale down here, going from -3 over here up to +3 over here. So 1.96 is just a little bit to the left of 2. So if I draw a line straight up from 2 and a line straight up from 0, and then I've shaded that area in. That area relative to the whole area, which we talked about was equal to 1, this area here that I've shaded is 0.475. So in other words, the probability of a standard normal being between 0 and 1.96 is 0.475, or 47.5%. So that kind of calculation, or that kind of result, is often summarized in something called a normal table. And the numbers inside that normal table, we have two different types of numbers. We have probabilities, and we have what are called critical values. So remember, the probabilities were the areas under the curve, and the critical values, that's what the numbers along the horizontal axis in this picture are. So the a equals 0 and the b equals 1.96, we can think of those as critical values, and then this area 0.475, that's a probability. So here's an example of a piece of a normal table. Let's look at the middle row first, the horizontal axis values. So these are the numbers along the axis. So going from 1.282, 1.645, 1.96, 2.326, 2.576, 3.090. These are critical values that correspond to specific tail areas. Let's look at the top row of the table next. So these are upper tail areas. So let's look at the point 1. So what that means is that if I have a horizontal axis value, a critical value of 1.282, the upper tail, which is the tail area to the right of 1.282, is 0.1 or 10%. The upper tail area to the right of 1.645 is 0.05 or 5%. The upper tail area to the right of 1.96 is 0.025 or 2.5%, and so on. The third row of this table gives a two-tail area, and you can see that all these numbers are simply the upper tail areas multiplied by 2. So what this point 2 means is that the upper tail area to the right of 1.282 plus the lower tail area to the left of minus 1.282, together those two tail areas add up to a two-tail area that's equal to 0.2. Let's skip to this one. This one is telling us that the upper tail area to the right of 1.96 plus the lower tail area to the left of minus 1.96 together comes to 0.05. So let's look at these examples. So I'm using the letter Z here, or Z, to represent a standard normal random variable. The probability that Z or Z is bigger than 1.96 is equal to 0.025. So that's this column in the table looking at the upper tail area. The critical value is 1.96. We could do a calculation based on that result if we were interested in finding the probability that Z is between 0 and 1.96. Okay, so how do we do that? Well, if the upper tail area to the right of 1.96 is 0.025, let's go back to the picture here. This tail area here, where I've got my mouse pointer, is 0.025. Remember, the whole area was 1, and this line in the middle divides it in half. So the area to the right of this line, all the way out to the far right tail, would be 0.5. Then this shaded area is going to be 1 minus 0.5 minus 0.025. So 1 minus 0.5 minus 0.025. 1 minus 0.5 minus 0.025. And that comes to 0.475. Okay, so that's this result here, 0.475. Okay, it's worth spending a little bit of time just mentally going through that if it's not clear. This shaded area we calculated as the entire area is 1. Subtract this piece over here, this white piece over here that's not shaded, that's 0.5. Subtract this white piece here that's not shaded, 0.025, and you'd be left with this shaded area here. So 1 minus 0.5 minus 0.025 comes to 0.475. Let's just do a few more examples quickly. Probability z bigger than 1.645. So that's asking for an upper tail area. We look up here, 1.645, the upper tail area is 0.05. So the answer to this question is 0.05. This next one, probability z less than minus 2.326 or greater than 2.326. That's a two-tail area. So that's equal to 0.02. And then the last one, this is kind of flipping that question. It's saying what number would have to go here to make this a true statement. So probability z less than some number equal to 0.9. So in other words, we talked about percentiles in the last video. It's asking what is the 90th percentile. Okay, so for this, we're looking at where the 90th percentile would come in this table. So the 90th percentile is going to come where we have 90% to the left, or 0.9 to the left, and 10% or 0.1 to the right. In other words, an upper tail area of 0.1. So we find the 0.1 in the table and look at the critical value that corresponds to an upper tail area of 0.1, and that critical value is 1.282. Okay, so that the number that goes here in place of this question mark would be 1.282. The 90th percentile is 1.282. So that's how to think about the normal distribution and probabilities based on a picture like this. We can do similar types of calculations for any type of normal distribution, not just a standard normal distribution, and we'll see that in the next video. So these types of calculation are only going to be useful if our model represents reality, if our model represents our sample. And so we need to have a way of assessing whether we have data that does look like it could come from a normal population. So one way to do that is to draw a histogram. Remember, we thought about a histogram as representing a normal density curve. So if we look at a histogram of the data, we could ask ourselves, does it look kind of approximately symmetric and bell-shaped? And that's one way of graphically assessing normality. It turns out that it's not a super reliable way of assessing normality because there's a little bit of arbitrariness about histograms. Because when we draw a histogram, if you remember back to the last video, we drew a histogram and we selected the intervals to be 150 to 175, 175 to 200, and so on. If we'd picked the intervals slightly differently, the appearance of the histogram could change, and sometimes it changes quite dramatically, especially with small samples. And so I find that there's a better way of assessing normality graphically, and that's to use something called a QQ plot or a normal probability plot. And these are a little bit easier to assess, in my opinion, because instead of trying to assess whether a histogram looks symmetric and bell-shaped, which is a kind of subjective, instead we can ask ourselves whether the points in a QQ plot or a normal probability plot, whether they lie along the diagonal line that's also part of the QQ plot. And there's a little bit of subjectivity there too, but I find it a slightly easier assessment to have to make visually. So here's an example. So here's a QQ plot for the home prices example, or a normal probability plot. And we're asking ourselves, do these points on the plot lie reasonably close to the line? And in this case, I would say, yeah, I think they do. Okay. Sometimes people will talk about, well, how close do you have to be to say they're reasonably close? Well, you can imagine laying a pencil down on the graph, like centered on that line, and if you can't see any or many points outside the thickness of the pencil, then it's close enough. So we can do this in R. So I'll show you how to do all of this in R. So we talked about the critical values and the probabilities in the normal table. So here's a way of getting those numbers. You use the qnorm function. So here's the numbers that were in the table we talked about: 1.282, 1.645, 1.96, and so on. And then to create a QQ plot or a normal probability plot, we use QQnorm, and then we add the line with QQ line. So you can see down here the normal probability plot or the QQ plot for the home prices data. So I've talked about population distributions, about the normal distribution and normal tables with critical values and probabilities in them. And then we've also talked a little bit about assessing normality using either a histogram, or slightly better is to use a QQ plot, also known as a normal probability plot.